All right. So if you remember last time, we were working on what do you call it? PID. I taught you guys the concepts of PID, how it works in the background, and how to tune PID, like a tuning process for PID. And then I found in the WPI lib simulator they have physics simulations, which means we can actually do a little bit of that within our own computers without actually having access to Doom Turtle or another robot. So I already wrote the code last night and we'll be going through it and following it. So let me just go ahead and just fetch that code. I need you to update, bud. Okay, there you go. Right. So you can see there's a bunch of code written here. Half of it is simulation code. But if we go and go to FRC VS Code, right? I had a weird bug last night where for some reason all of a sudden my Java failed to work. So um if it says like some sort of Java hat server failed on the bottom right of your VS Code, I'd recommend just pressing close workspace. That'll be under workspace and then and then open the folder, but don't open the workspace. That seemed to fix it for me. But let's just go ahead and simulate this code. And I already have my controller hooked up. So actually, let me see if I can. I'm not sure if I can. What's building? I can see if we can set up the I can see if we can set up the camera. Whatever. I'll trust you guys can see it. It'll be in the simulation. Let's go and just choose house and GUI. All right, this is our simulator. And so you can see here, I'm just gonna close network tables, other devices. I'll show what we're actually interested in, okay? So you can see here that I already have my controller. We're gonna pay attention to axis 1. I'm using the absolute value of axis 1. And basically I have an elevator simulation set up where basically if it's at 1, it's gonna go to the very top of the elevator, and if it's 0, it'll go to the very bottom. Okay, so you can control the position of the elevator. So I'm moving it. We have PWM outputs here, which shows you like the motor outputs, right? So that will be important eventually. And one more cool thing we're going to use is called Shuffleboard. If you're on Windows, you should be able to directly go into your start menu and then type in Shuffleboard. But I believe you can start Shuffleboard from here too. Oh, what was it like? I think you have to write. Yeah. So if you go here and you press Start Tool, and you can choose Shuffleboard. It's okay when we're actually coding later today. I'll make sure you guys are all able to do this. But the cool thing is, where's my Shuffleboard? There you are. All right, I'm gonna go to data. You can see I have a lifter position thing. I'm gonna go ahead and show this as a graph instead. Expand it. And then I'm just gonna go ahead and drag overlay the demand in here too. So basically demand, if you remember correctly, the way we try to design subsystems in our code is through demand so that it's easier to keep track of changes. So let's go ahead and just enable the robot. And right now I've set it so that the elevator's max height is 1.27 meters. You can see here, if I move it, you can see that the lifter position, the orange is what the simulator is holding it at. And then the yellow one is where I'm telling it to go. You can see if I let go, this is going to go all the way to the bottom. If I push it up, you can see that it actually ramps up and accelerates. You see that? And I believe that little bit of jiggle is just like error within the physics simulation or the encoder or however simulates it. But you can see, I spent the night PID tuning last night. You can see that it's pretty responsive to my changes. So, but basically, open up your IntelliJ and then go to where is it, build.gradle, and make sure that I'm going to zoom in here just to make sure you guys can see it. At the very top on line 3, make sure your version is 2021.2.2. Okay, so I need you guys all to go into your build.gradle and make this change. Actually, no. Actually, what we're gonna do is we're gonna go ahead and rebase my code. Okay, so stop what you guys are doing, and we can go ahead and do this. Okay, And let me see. I'll choose one lucky winner here. Choose Sunbreed. Okay, I'll use Sunbreeds. Pay attention, everybody, because this is we're gonna be basically updating all of our code on our local machines to be the exact same. Okay. So when you're in your current branch, and this means Sunbreed that you don't have to do this anymore. Oh, actually, I can just not push. But anyways, real quick, I'm just gonna update my local Sunbreed branch, right? And then I'm gonna go ahead and go into this branch menu. Oh, sorry. Go into branch on the top and then press rebase current branch. And rebase basically means take another branch and put it into mine. It's as simple as that. And you're gonna go in and just take Samuel. Okay, not Samuel teach, not Samuel temp, just Samuel. Okay, because this will update summary by applying blah 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 commits on top of blah, right? So let's press start rebase, and it says this warning require force push. It's fine, just begin rebase. And you'll see here, resolve conflicts before rebasing summary. And if you have any conflicted files, just use the modified file from Samuel, okay? Or it might say use the added file, okay? And once you're done, press continue rebase. And you can see, oh, wait, I have even more conflicts. Let's just do that. Use the modified file, use the added file, use the added file, use the added file, continue rebase. And then press continue rebase. And boom, there you go. You have all of your code updated to how we're gonna go ahead and start off today, and it just press force push origin. Okay. So I want to see all of you guys do that, and when you guys are done, can you guys give me the green check mark in the participants menu in Zoom? All right. So don't worry if you guys have any issues. Just watch and follow along. Okay. So we're going to be doing a few things that are familiar, which is joystick. We're going to go and get a motor. In this case, we're going to use a Victor SPX. That's another kind of motor. We're going to call this lifter motor. So if you remember correctly, if you've ever seen the robot before Doom Turtle, it's not called Poseidon. Anyways, the one we used for the 2019 competition, the lifter was actually powered by a motor, not a piston. So this is a little bit more like that. And then we're gonna declare a few constants here. You can still code on the side. Yeah, go ahead. We're gonna go ahead and code a few constants, which are encoder channels. And this won't apply when we're actually coding inside during competition, because we're going to be using encoders that are CAN encoders, so you don't have to specify the stuff. But if you're hooking up an encoder directly to the rubber reel, or in this case we're using it to do a simulation, you have to say the A channel and the B channel, and basically for now it's just 0 and 1, 2 or 3, 4 or 5, as long as they don't share. Okay, and then finally we're going to make an encoder. Now, I haven't covered encoders a lot in the past, and basically an encoder is pretty simple. Okay, so if you think about how motors work, they turn, right? And which means a motor is turning a shaft of some sort. And what you do is you hook up an encoder to that shaft, and the encoder will spin with it, and the encoder will be able to tell when it turns, basically, and how many turns it's done. Okay, and you can see here I have some red stuff, and I just import it. Right, you can hover over it, press import class, right? But basically encoder will be able to let us know where the elevator is right now. Is it all the way at the top? Is it in the middle, or is it all the way at the bottom? Right, so that's the job of the encoder, to tell us where we're going. And then one last thing, we're going to do public double demand is equal to 0, right? Because our demand is where we want the position we want to go, and you'll see soon. But basically, it's going to be from 0 to, let's just say 1 meter. Okay. All right, 0 to 1 meter. And then let's go ahead and actually no. I think it's better to do 1.27 meters. It's a bit of an odd number. And now we're going to go ahead and put in our simulation constants. Okay, so this is stuff that the simulator uses. So we're going to use this. I'm going to be making an object of class DC motor. I don't know why they decided to use the word DC motor for it, but they do. And basically what we're going to do is we're going to use a static method to basically say we're going to be using a gearbox that has one 775 motor. A 775 motor is a smallish type of motor, but it's powerful enough to get most stuff done. You just don't want to use it all the time. But basically, the bottom line is we're telling our simulation we're going to be using one VEX 775 Pro. Okay. And the next is we're going to say the gearing, the gear reduction. And this is something that you'll talk to the mechanical team or design team about. And I'm just going to be doing a sort of conservative gearing of 12 to 1. basically 12 turns in the motor will turn the elevator drum once. Okay. And then finally, or not finally, still a lot more. We're gonna be putting a constant as lifter drum radius. And basically right now, all we're doing is just defining constants, or basically just defining constants from our mechanical design over into the simulator, so that the simulator can mimic what we have in our real robot as much as possible, right? So I'm gonna go ahead and say the carriage is 4.0. You guys will probably be able to either measure directly with a scale or get it from the CAD. Okay, so again, that's something you'll interact with the other teams about. And then, so the parameters have already been measured. Yes, that's correct. So we're basically just putting in stuff that is already known to us. Okay, so physical measurements of the robot. Okay, and right now this is just some fancy math for encoder distance per pulse. Basically, an encoder will, if the coder reads 4096, it reads an inch or something like that. Right, and again, this is given stuff. Depending on the hardware you purchase and install, these numbers will be different, but they're all known numbers. Okay. So we have our simulation constants. Well, we're actually not done with simulation constants. We have a bit more. We're just going to go ahead and define the minimum height. So obviously the minimum height of the lifter is going to be 0. Static final double K max lifter height. And here is where we're going to say 1.27 meters, which happens to be 50 inches. Okay. And you can use this class code units is what WPI lib gives you. And it basically helps you convert stuff. So I'm converting 50 inches to meters. So this is in meters. This variable is in meters, right? And now we're going to go ahead and actually define the elevator sim. So we're going to go say private final elevator sim lifter sim. Okay. It's equal to new elevator sim lifter in, or sorry, new elevator sim. And then we're going to go ahead and specify a bunch of stuff. Okay. First thing first, I'm going to import. Right. And I'm going to go and specify my gearbox, my gearing, my carriage mass, my drum radius, right? My minimum lifter height, my max lifter height. And then this thing, which I'm actually, to be honest, not certain, but I just copy paste code for the simulator. It's probably worth it. Right. And end it with a semicolon, right? Oh, wait. Oh, right. Okay. That's the lifter sim. Basically put in all of our stuff. And then we're going to go ahead and say encoder sim, right? So this is our simulated encoder. And we're just passing our real encoder. And basically all this does is just import these. Basically these two are simulator classes, okay? Finally, we're going to go ahead and do PID controller. So this is our PID controller. And as I specified in our slides last time, we're going to set everything to 0, okay? P is 0, I is 0, D is 0. And we're going to be tuning P first, then we're tuning D first, and then finally I, right? And I'm going to go in and copy paste a few things, right? This is Shuffleboard. Let's just put in, it's what you saw in that GUI with that graph and whatnot, and this is how we send stuff to it. I'm just going to copy paste code into it for now, but basically, simply, you get a tab in the Shuffleboard, and you get a network table entry, right? So you in the tab you add an entry, and you say get entry, and you can update this entry, and it'll update the value in the Shuffleboard too. It's very handy for debugging. We use it a lot in real code. But anyways, that's enough for all. Oh, actually, no. There's one more thing. For the lifter, we're going to go ahead and make a constructor. So basically, we want code to run right when the subsystem starts. And we're going to set some things for the controller, which is this integrator range. It's just to make sure that the I term, it can't go crazy. And then we're going to go ahead and set the distance per pulse for our encoder, basically making sure it knows how to count. All right. And that's all of the initialization stuff. You can see there's quite a bit, and most of it, all of this stuff, is just simulation code. The rest, in real competition, is just this. Okay, but otherwise, we got our encoders, our motors, our joystick. We got our PID controller, and we have some things we can use to debug and add data, right? And then we have our simulation code. Does everyone follow so far? Okay, I'm going to go ahead and continue. All right, and first things first, as we always do, we have to read the joystick, right? So we're going to be changing our demand. So I'm going to say math.absolute joystick.get raw access. I don't really care if it's negative or positive, so I'm just going to say math.absolute. Take the absolute value of it, and raw is going to be a number from 0 to 1, right? So all I'm going to do is to get where I want to go, just do this. Raw times k max left or height. That's all you have to do. All right, it basically convert raw to desired position in meters. If I push the joystick 50% of the way, it will try to go 50% of the max height. All right. And then finally, we're going to use those network table entries to publish some stuff. We're going to go ahead and set our demand, right? And then we're also going to do lifter demand entry dot set double. Oh, I flipped these around. Right. Lifter position means we're going to read the encoder. So I'm going to say the lifter encoder dot get distance. Okay. This will put where we want to go and where we actually are in Shuffleboard. Oh, that's a lot of talking. Right. And now we're going to go ahead and I'm going to go ahead and use our PID controller. Okay. So we're going to say double PID output. We're going to save our PID output to another place. Controller.calculate lifter encoder.get distance demand. And then we're going to go in and clamp it like before. Math.clamp, or was it math utils? Yeah, math util.clamp. We're going to clamp PID output and we're going to limit to -1 and 1. Okay, so basically, yeah. So I'm going to go ahead. Finally, let's see. If demand is greater than 0.01, basically if we want to get more than a centimeter off the ground, we're going to go ahead and set lifter motor dot set. And speed is just going to be our PID output, right? And then else we're just going to go ahead and set our lifter motor dot set 0 because we don't want the motor to be making unnecessary moves when we don't want to go anywhere, when it's just resting at the bottom of the elevator. So that's what this is for. Okay. Finally, on disable, just to make sure when we disable the robot, the motor stops moving, we're going to say lifter motor dot set 0. Okay. And then here, this is a new one called simulation periodic. And when we did the fetching thing, I added a simulation periodic to the subsystem abstract class. But basically, simulation periodic is where we update our lifter. Okay, so I'm just gonna copy and paste this code. I copy pasted this code from the WPI lib website as well. But basically, import everything. This will let us simulate it, right? This updates this physics model. Are the parameters binary? Are you talking about which parameters? Which method, Yash? Lifter motor? No, you can set 0.3, 0.4, 0.5, etc. Because PID output will be anywhere from -1 to 1. So it can be 0.67, 0.89, etc., etc., etc. Okay. All right. So that's the lifter.java portion finished. We're going to go ahead and go to robot.java, right? And we're going to go ahead and put in some important things. We already have read periodic outputs. We already have write periodic outputs. But we're going to go and overwrite something new. Okay. I'm going to right click, generate, and then override methods. And then you should be able to override a simulation periodic. Okay. And what we're going to do is we're going to say lifter.simulation periodic. And I'm also going to do lifter.disable undisabled. There we go. All right. So this code will run if we're simulating it on our own computer. Okay. And then I think that's all we need, I believe. All right. So I'm going to go and open up my VS Code. I'm going to go here and press simulate robot code on desktop. Okay. And basically, we're going to be pit tuning today. So I'm going to be letting you guys pit tune. You guys will be saying in chat if chat what we should set this to and why not. And we'll do first come, first serve. Okay. And we're going to be pit tuning. All right. But first, let's go ahead and check. See, okay, my controller is working. Does the code crash? No, the code does not crash. Where's my, I need to see my PWM outputs. Where are my PWM outputs? Am I just blind? Oh yeah, right here. You can see right now, PWM1 is the motor we care about. You see it's not doing anything, right? And let's go ahead and open up Shuffleboard. Shuffle. Oh, right. I should probably show you guys how to open in ZS Code. Go here, start tool. I'm going to choose Shuffleboard, and the Shuffleboard should open. All right. Oh, you can see here client connected. That means the Shuffleboard connected to the connected. It's going to start getting data soon. Let's see, where's my Shuffleboard? Did Shuffleboard just crash? Oh, no, it didn't. All right, I'm going to the data tab. Aha, I can show this as a graph. You can see here the natural randomness of the encoder, and by extent, the encoders we have in our actual robot will be this squiggly as well. Just remember right now, it's 0.02. It's like barely wobbling. All right, now we're gonna have to go ahead and tune our P. So if you guys remember, or we're gonna start tuning our PID. So let's go ahead and start with the number P. If you guys remember correctly, I said that we should probably start with a small number, right? So why don't somebody give me a small number for the value of P? First come, first serve. Whoever says it first in the chat gets it. 0.25? All right, we're gonna start at 0.25. So I'm gonna go in and set the P to 0.25. I'm gonna refresh the code in VS Code. Right, I'm gonna open up my Shuffleboard. I'm gonna go and enable this. You can see that the motor's moving a bit. And oh, what's going on here? Let's not have it be weird like that. Let's to position show as graph. There we go. Right, you can see that the motor doesn't seem to be moving very much. Right, is it enabled? Yeah. So that probably means that we are going to need to we should probably give it a bit more. Can you refresh what PID is for like 2 minutes? Basically, PID is a way for it to move. Okay, it's a way that we can tell it to move and respond and to go there smoothly as well. So it seems like our PID value is a little bit too low. So does anyone want to try and increase it? Oh, what PI and D are? P is proportional, meaning the farther away you are, the motor's going to add more power. I is like if we're barely far away, it's going to nudge it. And D means if we're approaching it really quickly, we're going to slow down. Real quick, I'm just going to go ahead and make sure that I didn't screw anything up when I was writing the code, because I shouldn't. Right, okay. Hopefully we'll be fine. Okay, so if you notice, it didn't really move much. So that means we should probably give it, we should probably increase P. Does anyone want to suggest a new value for P? 0.3? 0.25 didn't move at all, so it would probably increase a bit more. Okay, let's go to 0.5. All right, I enabled. Oh, there we go. Look, at 0.5, we get something. But do you see how, like, so the yellow is where my joystick is right now, and the whatchamacallit, the orange one is where the elevator is right now. Do you see how severely under? Which means it's not very accurate at all. So that means we should probably increase P some more. Because remember, our first step in tuning is try to get P so that it's able to hold reasonably close to our desired position. So let's increase P some more. What do you guys think? All right, let's try one. Go enable. Ready? Boom. You can see one is a lot closer, but we're still not quite there. So what do you guys think we should do? 1.72. All right. Let's go and go to IntelliJ 1.72. Let's go ahead, refresh our code. Let's go ahead and enable. All right, you can see, I think it's getting there. Yep, it's close, but I think we can increase it a bit more. Any ideas? 1.8. Ideally, we can get within 0.1 meters of the target, by the way. That's what we want. I reckon we can get a little bit closer. What do you guys think? 0.1? Sorry, that would be making it worse. All right, I'm gonna go ahead and pitch something in, 1.9. I'm gonna go ahead and say, I think it's safe to increase it up to 2.8. I know it's a bit of a big jump, but I'm looking at how it responds right now, and I don't think this will make it go cuckoo yet. All right, so let's go ahead and enable. There you go. Hold on. Sometimes it doesn't want to update if the demand doesn't change. There you go. You can see it's a little bit closer now. Cook is when it's way beyond the target, right? Yeah, cuckoo. Right, exactly. Let's get just a little bit closer. Does anyone want to recommend a higher p-value? 3.5? Like that. Make sure I save. Refresh. Boom. All right. I would say, you know what? We're 0.5 off target, or 0.05. So only, what's that, like 5 centimeters? Only 5 centimeters off target. So I'm going to say that's good enough. All right. And just to demonstrate to you guys what happens when you have a massive P, let's just go ahead and just set it to 50. This is when you go too far. And this is probably, you don't want to do this because you'll probably damage the robot. You either burn out the motor or like damage some sort of hard stop. But if I enable, oh goodness, boom. Do you see how it oscillates like crazy around it? That's because it's reacting too strongly. It's going to go back to 3.5. So do you guys have an idea of how to tune P? Was that fun? It's height. So basically, this is what we'd be doing with the real robot. We'd be trying p-values. No, we don't. We deploy the code to the robot and we test in real life. But seeing how you're able to put in so many physical measurements, I might actually recommend you guys to try to use a simulator if you consider PID tuning in the future. When there's a season, of course. Okay, but check this out. I'm gonna bring it up pretty high up and try to. Do you see these oscillations? Do you see how it went up, down, up, down, up, down, up, down? So we're gonna try to reduce these oscillations, right? So our P gets us pretty close, but it overshoots it and undershoots, overshoots, undershoots. So that's the next step. We're gonna tune D. And as always, start a little bit small, but can someone put in a number for D? 0.5. All right. Let's go and enable teleup. Let's go and control it. Boom. Oh, wow. It looks like 0.5 might have done the trick. You can see here that it doesn't really oscillate that much anymore. You can see that it slows down a bit, but otherwise it doesn't overshoot or demand at all. So it looks like, you know what? This is a good number. If you're lucky and you get it right on the first try, there's no need to change it, right? Okay, but as you can see here, you might have noticed that we're ever so slightly off the target, right? We're always underneath that joystick curve, right? So let's go ahead and change that. This is where the I variable comes into play, okay? So, you know, I don't think I've heard from Wendy yet. Wendy, can you suggest a value for I? Sure, let's go and start with 1. Just a side note, my I is pretty big in the code I tested last night. So just to give you guys a hint. the only reason we're actually pit tuning really quickly right now, but that's partially because of the fact that with a simulator, we don't have to wait for the robot to boot up or anything. It's just super quick. But this might also means that you can deploy pit code to the robot really quickly. All right, as you can see here, the gap has closed a bit. Actually, that is really quite good. Hold on, let's go ahead and I'm gonna put the lifter position. I'm gonna do this. Hold on. So if I want to go to 0.6, oh my goodness. That is almost spot on. Wait, that's like perfect. Okay. Wow. But there you go. Do you see how closely it follows the how closely it follows my joystick? Uh when I change it? I'm changing it right now. This is me oscillating it. So in real life, if the simulator was a pretty good model, you would be able to see the robot go up and down with PID controller. Okay. And basically, this is how you tune PID. So that also means because of this, if we get plans to be able to go back in person into class, what I want to be able to do is have you guys try to come up. I'll give you guys the physical measurements for Doom Turtle, and then you guys can go ahead and try to model in the simulation, figure out what PID values work, and then when we're in person, we can go in and put those PID values in the actual robot, and then we can go ahead and see if your PID tuning was right or not, and if the simulator was close or not. So I hope this was kind of fun and enjoyable to all of you guys. I'm gonna go ahead and push this code, and I'm gonna let you guys catch up basically. So tune PID as a class, yay! And for the record, they have more than just elevator sim. You can see here. Hold on, let's go. Yeah, they have this classical linear system, and let's see what extends linear system. I'm not really sure, but there's a lot of stuff that extends linear system. Before I do anything, I'm gonna close that because the shuffleboard kills your computer. All right, what I want you guys all to do is simple. All right, I'm gonna use Wendy's as example again. Oh shoot, I can't anymore. Okay, you guys are gonna press fresh origin. When you guys press fresh origin, you're gonna go to your branch and press choose a branch to merge into, and just choose my Samuel branch. Okay, just choose origin.samuel. Basically, update your code with mine. Okay.